Recording is on.
Yeah, they said they can hear us. The students said in the chat they can hear you.
Okay, good. I should also ask the students if the live session is worthwhile too, because there's risks associated with it. There's technological risks associated with things not working. So one question is whether it's worth taking those risks. And the live session has any value versus properly recorded session. So anyway, I guess we'll begin pretty soon. How many people do we have now?
15.
15. Is that all we've got? I presume because there were 27 last lab. So we only got about half the people on.
It's not 10 yet, so we can wait for a few.
Yeah, we'll wait a couple more minutes. Okay, so I guess we'll begin. We've got 1, 2, 3, 4, 5, 15, 16, 17. We got 17 people on. So we'll try to record this, I guess, in case some people are missing it. Also, maybe in the comments, you guys can let me know if these live sessions are useful, because there's risks associated with trying to get everything to work. I find most things don't work nowadays. nothing built after the 1960s or 1970s works reliably. So there's risks associated with giving an online lecture because a lot of times things don't work, or they're unreliable, or the network doesn't work, or something's dragging or lagging. So if there is, if you guys can let me know if the live session brings value to this, I'll continue doing it, or if it's better to have a really good quality recording and do the recorded session. But anyway, I wanted to catch up on a couple of things from last time. I wanted to catch up on comparametrics, and what we did last time was comparametric equations. The labs were done well for the most part, but there were some common misconceptions and misunderstandings, and Adnan's lecture went really well recently, so I want everybody to hope everybody had a chance to look at that and go over that lecture material, because that would be very useful if you can go over that lecture material and understand Adnan's lecture. Just to really understand deeply what comparametrics is, because the next lab is superposimetrics. Comparametric equations are based on the linearity properties of light, and superposimetric equations are based on the superposition properties of light. And these are fundamental properties of physics. So there's a deep link to quantum field theory, quantum mechanics, and all those other things in light. If you can understand this and master this, I want to build a quantometric computer that can solve tough problems in quantum field theory that can't be solved in other ways. We can really leverage this and do some really wonderful things with it, starting, of course, with intelligent image processing and sensing. And so we're going to move into superposimetrics, where we superimpose images together. And so what I'm asking you to do for the next lab, lab 3, is to take one picture with one light turned on, and then take another picture with a different light turned on, and then take a picture with them both turned on, and confirm the superposition properties of light. And so the photocell experiment we already did touches on the linearity properties, and comparametrics. Now we're going to look at superposimetric equations, and of course, analogous to comparograms, there's superposigrams. And if you read up on that, you can go down that rabbit hole as far as you want to take it. So now let me go over to the other camera here and just kind of go over some simple concepts. So now, can you all hear me good? Let me know in the comment section if you can hear me clearly. So what I wanted to talk about briefly is, one thing is we had the photocell. So we had our camera consists of photoresistor, and we had our light source over here, and we successively half covered the light and uncovered it. So we had these results here, F of Q versus F of 2Q. And we made the simple observation that also alternatively you can use two light bulbs that are equidistant radially if the photocell is radially symmetric. So if you have a photocell like this, let's say, and that's kind of what they look like. And if it's radially symmetric, or at least bilaterally symmetric, you can put two light bulbs that equally contribute. So we can have one light bulb here, and we can have another light bulb here, and we can ensure that they're equally contributing, so that when you turn on only this light, you get a certain resistance. So if this is Q1 and this is Q2, we can ensure that F of Q1 equals F of Q2, and this gives us that Q1 equals Q2 for well-behaved F that's monotonic, and so we have a unique mapping continuous function F, monotonic continuous function. So now we have that if Q1 equals Q2, then we have, when we turn both lights on together, Q1 plus Q2, this will give us another value of resistance. And in the special case, that's F of 2Q, if Q1 equals Q2, which is Q, let's say. And more generally, we can confirm this. I think there's a package. Sorry about that. We just can't have any porch pirates. Get a lot of porch pirates nowadays, so just want to make sure nobody steals our package. So now we've got the Q1, Q2, F of Q1 plus Q2 equals F of 2Q. And that is, allows us to go down this path. So now we can move these lights closer. So what we do is we move this light closer until it gives the same as what both lights got. And then we turn it off, and then we move this light closer until it gives the same as what both lights got. And then we turn them on together. In a way, this is kind of superposimetrics. What we're doing here is in some ways, this approach here that we had, this is comparametrics. Grab a different marker. This is comparametrics. And this approach over here is superposimetric. This is superposition here. And you can see that comparametrics is a special case of superposimetrics. You can see this is just degenerating to one special case, and we've gone down the locus of control. More generally, we could take a whole bunch of points like F of Q1, F of Q2, F of Q1 plus Q2, and we could vary these over a complete three-dimensional space. And we could construct what we call a superposigram over that full space, kind of going through the space. So that is kind of where we're heading, because the next logical step with Q1 and Q2 is to now take this here and say we have, let's say we're going to have, let's call this Q1 here. See, this is Q1. And then we're going to take another light bulb here, and we're going to move that light bulb around, shut off this one, and turn on this another light bulb here and get it to equal, so that F of Q1, say this is Q2, and then we put another light bulb here, the third one, and turn this one off, and then turn this one on. This is Q3, and then we turn that off and turn this one on. This is Q4, and so on, and Q5. And the easiest way is to put these around, and let's say Q6. And then what we can do is we can turn 5 of them on, so we can determine F of Q1 equals F of Q2 equals F of Q3 equals F of Q4 equals F of Q6. We can turn them, we can confirm that, and then we can turn 5 of them on and measure that. And this is just F of Q, and then we can unwrap this to a finer degree. We can unwrap this comparagram to a finer degree. We can have F of 5Q versus F of Q, and now F of 6Q, with F of 5Q versus F of 6Q. And that's starting to take us, this limit, we have F of 1 plus epsilon times Q versus F of Q, i.e. K equals 1 plus epsilon. So we can see we're growing K slightly, and there's something very profound about this in the limit. as we will soon realize. So just going over this lab, this last lab, I think everybody got this last lab quite well. There is a couple of misconceptions. I mean, one misconception is what happens at the origin. So the photocell, as you shine more light on it, so that as you increase the light, increase Q, then the resistance decreases. So the resistance becomes less as you increase the Q. And so what would you expect when it's totally dark? What would you expect the resistance to be? Well, the resistance would be very, very high when it's totally dark. I think one person said, oh, at the origin, we're going to have 0, 0, which is 0 ohms at 0 light. And that's not true, because it would be approximately 0 conductance at 0 light, or infinity ohms. Conductance is the reciprocal of resistance. And you'll see in a resistance meter, and I think these digital meters don't do justice. I think that when people who grew up with analog meters understand resistance, but people who grew up with digital meters don't understand resistance, because in an analog world, you know, the old style meters, you'd have your resistance meter. It actually said infinity right on here, and it would say, you know, 1 meg, 1 kilo ohm, you know, 100 ohms, 10, you know, and then 0 ohms would be over here on the right. And there's a resistance scale written on there that kind of made sense, and you kind of get an intuitive understanding for what this all means. Whereas here you don't actually see that movement or that progression to infinity. So that's something to keep in mind. The second thing to keep in mind is that sometimes the resistance isn't that high. Some photocells do have a lot of photocells have a resistance that's so high that you can't measure it. And I've got a number of meters. This is a Keysight resistance meter. It's a little bit better than the average resistance meter, and it has a USB interface that's optically isolated for safety. It has an optical isolator, and it plugs into USB, so you can data log with that. And then I've got these other Keysight instruments here that, and the funny thing is that indicator is an off indicator. Modern equipment, the indicator comes off when the unit is up. The indicator comes on when the unit is off. And so this is what a modern resistance meter looks like. You know, you got this, it comes up Keysight Technologies, and it'll show a resistance. And the Keithley is the other, the classic good meter is the Keithley, you know, one of the best meters. Traditionally, those were with Nixie tubes. And now it's got, now these have, you know, more of a modern display on them. And so you can see now the numbers appear on the screen. And so that allows us to measure the resistance. And what we find is, even with a really good meter like that, that goes up to a gig ohm, a good photocell, when it's in the dark, if you wrap it up in a black cloth and put it in a black closet, in a black room with everything covered up black, as dark as you can make it, it'll go past 1 gig ohm. It'll become unreadable. It'll go beyond what the instrument can measure. So it's pretty close to infinity. So it's pretty accurate with some photocells to say that if you plot conductance, let's say Q, and 1 over R, which is conductance, then it's pretty safe to say that we're going through the origin with most photocells, but not all. Some of them, like this one here, this photocell is actually about 10 kilo ohms in the dark. So it actually has quite a bit of side resistance. So there's a, you know, alpha plus beta Q to the gamma is a pretty good reasoning here. And this, what you have is the alpha. Alpha is 0 on many photocells, which is nice because they do pass through the origin. And then you can force it through the origin when you're doing your line fit. But it's not always. And that means the comparametric plot, comparametric plot will be a straight line. This is F, and this is G. And it'll pass through the origin under this circumstance here when we're on 0, 0. But otherwise, it may have a slight offset. It doesn't pass through the origin. So you may want to not assume it passed through the origin unless you verify that. Don't just put 0, 0 into your plot and say, oh, when the light is 0, the conduction is 0, you know, 0 infinity ohms. But instead, just confirm that before you introduce that data point into your data set. Otherwise, it'll pollute your data set. So make sure your assumptions are valid when you're doing these sorts of things. The other thing is I want to go through a simple worked example here. Most of these photocells, for most good quality cells, or even the ones that are only 75 cents, most of them are quite good. Most of them will have something like F equals alpha plus beta q to the gamma, and a lot of times alpha goes to 0, and you can confirm that. But do confirm that before assuming that. But let's say we get lucky and it comes up that way. Then what you have is F equals beta q to the gamma. And now what we typically, and we can't really know what beta is, it's an unknown constant. So let's just without loss of generality, because this will have the same comparograph, let's say that it is, just on my time there, it's 8:30 now almost. So if this is F equals q to the gamma, and so now you want to think about, okay, what is a typical value of gamma? And it's, somewhere a good value. Let's take a simple example. Let's take gamma equals 1/2, because that's a fairly realistic example to think about. I want to work through a really simple example. I love to come up with really simple teaching examples because it makes it really easy to understand. So this is your function of q. F equals the square root of q, and there's a constant there which we can't know. I'm just leaving it out for simplicity. So now g equals f of kq equals the square root of 2q, which equals square root of 2 square root of q, which equals root 2 times f. So we have g equals the square root 2 times f is the comparametric equation. And so this is what we observe, and we don't know what this is. Let's suppose we don't know what that is, and we want to kind of understand this. So given this, what can we determine about f of q? And so one way to do this is to kind of, as we say, unroll this comparagram and sort of solve it, like kind of unwrap it or unlock this mystery. And so let's say I'm going to plot an example here. I'm going to take my graph here, and let's say I'm going to just take a simple example. I've got, draw a line here. Hold this steady, see if I can get lines here. Let me go like this. Right here. I'm going to go like that. My graph paper. Make another line here. Another one here. And so this is, I'm just constructing how I'm going to graph this out. And I'm going to take this really, really simple example here. So 1, 2, 3, 4, 5. 6, 7, 8, 9, 10, 11, 12. This is where I'd be better off to record 13. 14, 15. 16. So now I've got, and the reason I chose 16 is because it's a nice number to work with. And we can, got these little magnetic holders to hold my markers on the table. That'll make it a little faster if I go like this. I'm just going to draw one. So I'm squaring off an area here. And what I want to do is I want to highlight how simple this function is. So the slope of, think about, ask what is the slope of the graph? So I'm doing g as a function of f. What is the slope of that graph? So this is a good example. You want to work through a really simple example like this and really understand it, and then go back to Adnan's lectures, because this segues nicely into Adnan's lecture series. If you can understand this in a really simple way, you can understand quantum field theory. Actually, it goes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So now I've got a scale here, and we're going to plot that photocell. So this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and one more will give us 16. And that's a good place to stop. 16. So there's 16. So I got this grid that's 16 by 16, and I'm going to, and I almost want to add a bit more to it and make it go up to like 22 or something. 16 across by 22 high will sort of work out nice. So now we want to draw here a line of slope, and the slope will be dictated by what is the root 2. So if you look here, you're going to have a series of points. We're going to have, when we come over 1, this will be up the root 2. When we're over 2, it's 2 root 2, which is 2.8. And you can see at each point, and then you can see at each point, like 4 root 2 is 5.6. So you get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, so now you can see each of these, 5.6. So you see each of these is going to be root 2 more, and these numbers will seem familiar if you're doing a lot of photography or whatever. So you get 1, 2.8, and then you're going to have 5.6 is about here, and then 8, you're going to have it 8. It's going to be around 11 and a bit. And so you're going to see that there's going to be this line here, which has a slope of the square root of 2, connecting these points together. And so that's your underlying line that you're tracing out. Now, as you trace this out, you're tracing it out in steps or increments. And so you kind of unroll this. So the question is, given this comparagraph, what is the underlying comparametric function? So when you think about it, you're going to have f of q0. Let's call this q0 at the 1. I'm going to relabel that axis. And without loss of generality, I'm just going to take whatever the first resistance is. And conductance might be an easier way to think of it than if you take 1 over resistance. And I'm going to just call that first quantity of light Q0. And we don't know what that quantity of light is. All we know is the amount of conductance that caused that it causes. So we know the amount of conductance that it causes, but we don't know what that is. And then now, when I take root 2 times Q0, and so here we've got, this is f of q, and So this is our, corresponds to Q0. This is f of Q0, and then this is f of 2Q, gives rise to this quantity of light, and we know f of 2Q is root 2 times as much. Now, if we take that much and come over, the process of doing the experiment, when you take your photocell, when you either turn one light on and then turn them both on, and then take that number and move forward, the process of iterating is like drawing a circle here of that radius. So that's a circle of radius 1.414, whatever, root 2. And that comes down to root 2. And if we come up by root 2 right here, we're going to hit that line at exactly the point where it's 2. The line is exactly 2. And so over here, and this is the next one. So this is Q0, this is Q1, and then if we take this over to 2, this circle is going to come down to the radius of 2, and then we're going to go up here, and this is going to be 2.8 over here. So this is at 2.8. And then if we take that radius of circle of 2.8 down to here, and we go, this is f of q in this axis, and this is, draw one more. And this is right here, f of 2, this 2.8 happens to intersect the curve at exactly 4. So it comes up right at 4, bang on 4. And if we take a circle of radius 4 and we draw it down here, we drop this one down to here, an arc. What we're doing basically is taking that distance here on this axis and moving over that distance on this axis. In a sense, what we're doing is we're just going to the next axis. And then so now we're going to go up here, and this hits this axis at exactly 5.6. And then we're going to take that arc at exactly 5.6 and come up to here, and then this arc goes up at 5.6, and it hits this graph at exactly 8. So this comes over to exactly 8 here, and then we take an arc of exactly 8 down here, and it comes over here at this point. This is 8 right here, and when we go up to 8, it goes like 11 point something, 11.3 or 11.1, 11.1 roughly. And so you can see each time, and then if I take this at 11.1, it comes down, it's going to meet around there. And if I come up at 11.1, it hits this graph right here at 16. Actually, 16 is over there. It's this graph at 16, that just meets right there. So it hits this graph at 16 here. So you can see I'm kind of unrolling this comparagram. So I'm unraveling this mystery. I've got this curve here, and the underlying response is a mystery, and I'm unlocking this mystery iteratively in small steps. You can see that I'm sort of solving it. And you can kind of understand that each time I unroll this, I get new data. So now what I'm going to do is I'm going to have my answer. I'm going to have my f of q, whatever is f of q, the secret mysterious function f of q. I'm going to have this. I'm going to know it at a series of points. Like I'm going to know what it is at. So I'm going to know what it is at Q0, at 2Q0, at 4Q0, at 8Q0, and so on, 16Q0. And so for each of those, I'm going to have a value. And what I'm going to realize here is that I'm going to discover that this is a square root function sampled at these points. So this is, each of these is the square root of that function at these points. But I'm only going to know it at these points here. Now you can see if I make that comparametric ratio smaller, I'll know it more finely grained. You probably saw when you did the experiment with k equals 2, you got to see this function at only a few points. When you did the experiment with k equals 1.2, you got more points. When you did k equals 14 over 13, you got even more points. When you did k equals 40 over 39, again, you got even more points. So each time you have more. So if I had a ring of lights that had 101 lights on it, and I turned on, 100 lights, and then I turned on one light, I've only got a 1% increase. So epsilon is 0.01. And you can see in the limit as epsilon approaches 0, you're going to discover that function completely and unravel the mystery of that function totally. So that is what Adnan gave you, is Adnan took this concept here, which is we normally think in discrete form, and did it continuously. And that ties into quantum field theory. Very, very important discovery in quantum field theory. So I want everybody to really understand that, very deeply. And a couple of simple examples. I'm going to give you some homework. Just for fun, if anybody wants to really understand this this process really clearly. There's a couple of examples. I'll give you some homework. It's really easy. So I've got really, really easy to solve comparametric equations. And I'll just grab a shot of this too in case there's going to be a couple of people who probably missed this lecture, and I just want to make sure everybody has this concept in their head. I'll try and draw this a little bit nicer when there's time, when it's possible to draw it. And so now, give you some examples to think about here. I want everybody to think about some really easy comparametric equations to solve that will make this problem crystal clear in your mind and understand it. And so this comparametric equation was designed for ease of solution rather than practicality. And so let's go g of f equals square root of f squared plus 1. And you can see as you iteratively apply that, as you continue to apply that, you can say like, okay, f2, let's say f2 equals square root of f1 squared plus 1. And then at the next iteration, as you continue to unroll this, f3 will often say, we'll go q1, q0 is your reference q, and then q1, q2, q3, q4. We'll go f of q0, and then g. So you're gonna think like this. You're gonna think of f of q0. So I'll call it f0, and then f1 is f of kq0, and we'll define let q1, your next quantity, equal kq0, and then q2 is kq1 is k squared q0, and so on. And you can see that we're applying this again and again and again, just like Adnan's lecture. So you're gonna say now f3 is the next one, is going to be the square root of f2 squared plus 1. And so you're going to take, this is f2 squared, square root of f2 squared plus 1, and that equals, you can see the square root and the square cancel. And so you can see it's going to be square root of f2 squared plus 1 equals the square root of f2 squared plus 2. It just very nicely works out. And then you're going to see f4 equals the square root of f, and it's going to pick up another constant. So each time you iterate, this number is going to just increase by 1 each time. So you'll see a pattern there, and it's really, really easy to solve that comparametric equation for that reason. And that particular comparametric equation will help you understand, if you work through that example, will help you understand generally how comparametric equations work. And there's a couple of more simple examples, like you can say that g of f equal, f to the 5 plus 1 raised to the 5th. Any of these things that undoes each other works nicely like that. Or let g equal log base 2 of 2 to the f plus 1. That's another example. Or let g equal f to the gamma plus alpha to the beta, where beta equals 1. That's another good example. Or let g equal tan arctan f minus beta, let's say. So there's a couple of examples you can work through that will make this understandable and make it really easy to follow. And if you go through a couple of simple examples like that, I think something will click in your head, and you'll start to be able to really see and understand what Adnan's showing in that lecture. Once we understand comparametrics, we can move on to superposimetrics. So moving right along to superposimetrics, you have your camera response. You have, inside the camera, remember there's this implicit compressor. The camera has something like this. It captures data. We have this dynamic range compressor. Maybe it's a square root function like what's in that photocell or in a real camera. And then this is coming out here, and it comes out here. And let's say we have a second camera. This is the same camera at a different point in time or a different point in exposure. And so these two cameras are the same camera. Let's say this is the camera with one of the lights turned on, and this is the camera with another light turned on, and then the third camera is the camera with both of them turned on. And so what we're going to do is we're now going to expand this. So let's say you square each pixel value in the array, and then you add them together, and then you take the square root and compress them again. So we're going to expand, sum, and compress. By compression, I don't mean JPEG compression to make the file smaller. What I mean is compression to reduce the dynamic range. That's called dynamic range compression. It's often, in audio, it's fairly common. There is here, I have a compressor limiter, for example, in audio, and you switch back to this one, you probably see it here. You can see a little bit of it here. I use that sometimes for my microphone. So this is a compressor limiter. You can probably see that there. And that limits or compresses or limits the dynamic range of the sound. Vacuum tube amplifiers often do that inherently. So that's what we mean by dynamic compression. This is what a tube amp does, like data compressor limiter. This is one right here. Even I'll pull this out so you can see it a little bit better. This is a compressor limiter. It has actually a vacuum tube in it, and it uses that compressive response function. And there's this debate about whether tube amplifiers produce better sound or not, and it really depends on what you're trying to do. But tube amplifiers, I remember in the old days, if you had a radio and you turned the volume up and up and up, the radio would get louder and louder and louder, and it would hit a certain point where it kind of got a little quieter again as you increase the volume. Whereas a transistor amplifier, when you turn it up and up and up, it gets to a point where it sounds awful and clips and distorts at hard limit. It hits its limit very hard, whereas vacuum tubes sag gently. When they hit their limit, they just gently kind of droop down and gain a little bit. And that's called compression, dynamic range compression, and it sounds pleasing. A transistor amp and tube amp will both sound the same at low volume, but when you play them really, really loud, the tube amp will always sound better because, for the most part, because it'll ease off, it'll compress the dynamic range a little bit. In photography, we like to compress the dynamic range hard. When you get to white, you know, if you have somebody's skin tone and all of a sudden it clips to white to 255, it looks terrible, whereas film has a softer limit. You can keep exposing film and it won't hit the limit as abruptly. And so that's why cameras often have this compression in them to make them hit the limit in a nice way. So you want to first expand those compressions to do the exact opposite of what Stockham said, add them together and then compress the result. And one simple law in terms of expand is to square them, and this can be a square root. So inside the camera, let's assume there's a square root function, and we're just going to square it and then add them and take the square root. We could also do the cube root and then cube it and then take the cube root again. We could assume that maybe there's a cube root function here. So what I want you to do is to take two pictures, each differently illuminated, compress them, or expand them, I mean, add them and compress them again. And I want you to try different values and plot a graph of that exponent. So let's say the exponent is 2 or 3 or 4 or 1. When the exponent is 1, it's the identity map. There's no change. So when the exponent is 1, you just add the two pictures together and do nothing here. Do nothing here and do nothing here, except just in the limit when the exponent is 1, it becomes the same as just adding the two pictures together. And of course, that looks horrible, but you'll find that, you'll see that. I want you to see what happens when you just add two pictures that are differently illuminated. It won't look like the lights are turned on together. So you take a picture with one light turned on. You want some overlap in the lighting. You want one picture to light one side of your room, the other picture to light the other side of your room. There's some overlap. Turn one on, turn the other on, and then turn them both on. And then you'll get this nice effect. You'll see that. So the first part of the lab is just to reproduce that experiment and plot this graph, and you'll see it'll dip down somewhere. The error, what I want you to do is to take, so this camera here has both lights turned on. This camera here has one light turned on. This camera here has the other light turned on. So you might have a desk lamp turned on here. You might have the ceiling light turned on for this picture, and you have both lights turned on for this picture. And I'll call this, say this is F1, is F of Q1, and we'll call this, say, F2 equals F of Q2, and I'm going to call this, say, F3, let's say, equals F of Q1 plus Q2. And then what I want you to do is take this image over here, and we'll call this, say, F12. And what we want to do is we want to take F12 here is going to be a picture. It'll be maybe 42 megapixels or whatever. This is F12 here, right there, and then this is F3 over here. And then what I want you to do is see when they're most similar. See what value of P, what exponent P makes these two look most similar to one another, or be the least. You'll get a numerical result. You can plot. This is the error, the error squared, let's say, and it'll go down to the lowest and then go back up again. And the question is, where does it reach the lowest? What's the value of P that gives you the lowest error? So that's your first part. Second part is we're going to do artistic overlays. So one of the things is we're making a heart monitor, and so we're going to overlay this data, and we're going to be able to understand health. So one of the things we're doing with wearables and overlays and data in the eyeglasses is mapping things. So I like to exercise a strong, healthy heart. So what I do is I run and swim every day that I can, every day that it's safe to do so. If it's treacherous, sometimes the roads are icy and it's dangerous to run. And sometimes there's a real storm in the lake and there's pieces of ice floating around. You can really scratch yourself up and swimming in ice fragments at high winds and get hammered by the ice. So you always play safe. So the best thing is I always like to have negative risk. So I want to do the exercise at negative risk so that doing the activity has less risk than not doing the activity. Because there's risk of staying sedentary if you don't get exercise. Heart failure is the #1 cause of death. If you don't get exercise, heart failure comes really close. But if you get regular exercise when it's safe to do so, you reduce the chance of heart failure. And I like to know how far I can push my heart. When you run hard, it pushes your heart. And when you swim in ice water, there's a lot of health benefits to ice water swimming. And this time of year, of course, the pools are all closed and you swim in the lake. And so there's about 250 of us who are part of a small community called Swim at Ontario Place. And we swim in the lake and want to monitor our heart and see what our heart's doing, see if the cold water is helping us. Sometimes if you've never done it before, you jump into the cold water, you have a real shock reaction, your heart skyrockets. But as you get used to it, you can learn to stay calm and sort of pace it out. And so we want to measure that and overlay that electrocardiogram. So I've got a heart monitor here. So this is my heart monitor, which I put in the pipe. And pipes are good at keeping water in, and they're also good at keeping water out, presumably. And so I've got this in a pipe fitting. And there are 4 electrodes on this one. Some of them have 10 electrodes. And so you put that heart monitor, and I'll show a little bit about background on the heart. I'll just touch on that briefly, but I don't want to spend too much time because you can look this all up. You can search this all up all over the place, and I'll post some material on it. But you got your let's see if I just switch back to the other side here. I'm going to switch to the other camera. And back to here. So you've got a device like this that allows you to connect electrocardiographic content, and then it's going to be displayed. Traditionally, electrocardiographic content is displayed on an oscilloscope, like a bedside monitor that you'd have when you're in a hospital or something, but now wearables allow us to take it everywhere. But this is typically what an oscilloscope looks like. I'll turn the lights down so you can see the trace a little bit better. There's a trace there, and the speed is here. There's modern devices like this here. This is a Keysight. This device here, I call this an Electroscope because it alleges to be an oscilloscope. It's really just a computer system that has display built into it. But an actual real oscilloscope has a cathode ray tube in it, electron beam, and it shines. The electron beam comes up the screen here, and you can see that data, see that information displayed on here in real time. And so you can pick up your heartbeat, and you don't want to try this at home, of course, without the right safety, because you don't want to connect what has voltage into your heart, but you want to do it safely, which means having a good isolated input. And so the oscilloscope has a good isolated input. It's always a thing to have. And so we will overlay heart information. So what I want to do is overlay electrocardiographic information on top of reality using the computer-enhanced multiple exposure numerical technique, CEMENT. So wearcam.org/cement.tgz, short little thing I put together. It's kind of badly written. It was original Fortran code that I threw together like 30 or 40 years ago. And then we moved over to C about 30 years ago. And it's sort of badly written C code, so it's not something I'm really proud of. But it does work, and it's simple. And feel free to rewrite it better, of course. And it just basically composes 2 images, computer-enhanced multiple exposure numerical technique. So it does Lab 3 for you, in a sense. You can just do Lab 3 in Python probably just as easily, or whatever your favorite modern sort of programming environment is. Put the images together and overlay. So I've got some images that I made. I've got an electrocardiogram I recorded from my heart here on this device as a picture. And then I've got some heart rate that I recorded on Nixie tubes. These are light bulbs. These are special little light bulbs that light up. See, they have numerals inside them. And these light bulbs have filaments. There's 10 filaments inside each of these light bulbs. And the filaments are in the shape of numerals. And so they glow with the numeral. That I kind of like those because they're nice glowing light bulbs and they show the numbers. So what you want to do is overlay the Nixie image that I've got picture of the Nixie, and then overlay that on top of the picture of the cathode ray oscillograph and create what is a visually appealing thing. And the question for your second part of the lab is, which is the most visually appealing overlay? And then finally, once you've done that overlay, visually appealing, then pull out the data, the actual electrocardiographic data, and overlay that. So you can do that in GNU plot. Plot that as a green line on a black background, and then use cement to put that in. So first you cement what's the picture of the oscilloscope screen, and then later you'll cement what is, you'll generate your own trace from your own cardiographic data if you want, or you can use my data. I posted some of my data on one of my run swims. The data is all over the place. It's kind of garbage because the thing's gone all over. I'm running hard and these things are knocking around. So it's not all good, but you can go through and find a piece of the data that's good. So I want to see overlay of that electrocardiographic waveform plus an estimate of the heart rate overlaid on top of the video. Just choose a short segment of video because it's tough to deal with video files that are big. It's 4K video with sound. So if you can take a short segment, like a few seconds long, and just overlay the cardiograph, and maybe you can scroll the cardiograph. So this is your chance to artistically show what a good dashboard is for the human health. So you want to use this information you're learning here about superposimetrics, how to create a visually appealing display and overlay. That's kind of what augmented reality does, is it adds stuff together. So you want to add light. So what I'm seeing through my eyeglass, so my eyeglass is running while I run, my eyeglass is recording the data of the run. And then my heart's also recording, and I want to see that kind of overlaid and see if you can mimic the artistic and aesthetic appearance of this cathode ray oscillograph with the Nixie tubes, get something that looks similar to that, where you've got this glowing data added onto the reality. And that's kind of this idea of augmented reality, where it appears to glow. You want everything on a black ground. You do all your plots on a black background. I call that a black ground. So you want your plots glowing lines. Usually what I do is I plot a big fat line that's kind of dark green, and then I plot a thin green brighter line on top of that and a black background using GNU plot, and then I cement that on top of the live video feed so that you get this nice photorealistic rendition that's very similar to what I used to do, is have these tiny little cathode ray tubes in my eyeglass. I made a real miniature version of that showing my electrocardiogram while I was jogging, overlaid on top of my reality. So you kind of get that look. See if you can achieve that nice look, that artistic visual aesthetic using cement and superposimetrics. So yeah, let me know if you have any questions. Feel free to reach out if you have trouble reading the data or something like that. Then let me know, and we'll take it from there. I just want to make sure, see if I got any comments, I think. Oh, some people were understanding Adnan's lecture. Can everybody hear me? I hope everybody heard me, because I got a couple of comments. Yes, okay, that's good. And then I did not understand how Adnan's lectures connected. So hopefully, I'm hoping these simple examples, because a few people were asking about Adnan's lectures, and what I really want to do is show those simple examples. Like try and do that. So try and connect and understand Adnan's lectures if you can, and understand this. This is simple. This electrocardiographic stuff is really, really easy. So if you try to measure your heart, you'll notice it's very, very noisy. It's kind of a weak signal. What you do is you have electrode paste or electrode gel here that you put on these little things here, and you can buy cheap little stick-ons at Home Hardware for 75 cents each. Just be careful. You don't want to have any voltage present on them from anything. So you don't want to have them near anything that might produce voltage, because you don't want to have your heart fail when you're trying to measure it. You don't want to change what you're trying to measure. And so if I put this onto my heart, you'll see it there, and it's pretty noisy. But the thing is, I need a ground signal. So that's what's missing from this. That's why it's so noisy. You can see that there. It's really, really noisy. You can hardly see it at all. And then if I take this here and put a little bit of this on there and put this other wire here which is grounded anywhere almost. It sort of doesn't matter where it is. And then I put this on here with the positive towards the outside and the negative towards the center usually. Then it'll go up when you're trying to go up. And now you can see my heartbeat there. Let's position them into the right spot. And you can see that persists on there. And if I slow it down a little bit, you can kind of see it there. Can everybody see that? I don't know, it's kind of far away, it's hard to see, but I'll put some close-up shots of it there. So what I did is I simply, I bought this beard trimmer and I shaved the rug off everywhere. I shaved completely with the beard trimmer, and then I used a short, close razor, very close razor to get a really clean shave, and then I scrubbed, had a good shower, and then after that put some rubbing alcohol, isopropyl rubbing alcohol, to get like isopropyl alcohol wipes, and then finally good quality electrodes. I got on Amazon, pack of 100 electrodes are good, or you can get them at Home Hardware for 75 cents each. And but you always have to be careful when you're connecting stuff to your body that none of those wires, because if that wire touches something that's electrical, even a small voltage can be very fatal. So you have to not try this sort of thing at home, or make sure you really know what you're doing. But anyway, so I've got that data, and I've got some cardiographic data that you can overlay, and I'm hoping that everybody will have fun with it. So any other questions? And just post anything in the comments that you want, and I'll try to get back to you. And otherwise, we'll meet up, check out the lab. Hopefully do the lab early, because you want to get it. If you have any questions, you want to be able to ask them. Any questions you might have, you want to be able to ask those questions early on, so that you've got lots of time. And okay, so that's it then, and we'll hopefully see you all soon. We're going to have our lab on Monday. Again, we'll do the same thing as we did before. We'll have everybody present what they've done and get an instructable set up for the cement. You can see the graphs in the instructable, try to understand that. If you're having trouble understanding addend stuff, first get a really firm grip on the really basic things, like do that example I had with the square root of 2, go through that example and unroll it and just push that all the way and really understand that. And then go through the 2-light example with the different power exponent values and try to find the minimum and plot that out. Go through the instructable, make sure you understand all this stuff really, really well. And then try to overlay, have some fun. I'm looking for who can be artistic and expressive on the overlays, because we're looking for new people to join our project. We got summer jobs here in various companies. There's a bunch of stuff in Silicon Valley. We're doing heart monitoring all over the world. In Shenzhen, we're designing heart monitors. So if there's anybody who wants to jump into wearables and can do a head-up display with an eyeglass-based heart monitor that overlays or something like that, that'd be super awesome. So yeah, show your ability to understand and what you can do. So now, if anybody has a midterm or anything like that, and also maybe I'll make a little tutorial on how to run cement, because I see a few questions on that. And there's an example of an overlay. By the way, if you go to Lab 3, you'll see the example of the overlay. I've got my screen shared. I should be able to just walk quickly through Lab 3. Hopefully I don't want to go over the lecture too much, because let me know if you guys have anywhere else you have to be right now. But if I go to wherecam.org, actually we have a lab slot anyway, so we can probably go over the lecture a little without detriment, because there's normally a lab scheduled. So now wherecam.org/ECE516, you go to here, you go to /lab 2021.htm. Superposimetric image processing is right here. And so you'll see, somebody said, is there an example? So there's an example right here. So here is what I see through my eyeglass. This is a straight out of my eyeglass, 4K 60p video right off my eyeglasses recorded. It's a still frame using a still frame grab. Here is an oscillograph. This is just a photograph right off of my cathode ray tube. This is a photograph of Nixie, and this is what the overlay looks like. So to me, that looks pleasing. It's artistically, aesthetically pleasing. It looks like that's what you want to show with the cement, to cement that together. And then, so what p-value results in the most natural looking image? And then you can take the data from the actual data set. If you go here, you'll see there's a run swim shown here. This is the data set that we have available. There's some of the data using just a GNU plot, or as is actually Octave, which is kind of like MATLAB similar. And so this is an electrode placement here. And this is...
Steve, you're not sharing your screen.
Oh, how am I not sharing? Oh, hang on a second. How am I not sharing my screen? I thought I was sharing.
You're in Jitsi. You're in OBS right now.
Okay, so let me go to total then. Let me go to total. I got so many messages I can't get to the button thing that needs to share the screen. Oh, there it is. Now, cancel share screen, and I'll share it again. Entire screen. Okay, can you see it? We good? Go back. Is the screen sharing?
Yep.
Okay. So now superposimetrics. So we're going to do part A is simply to do two pictures with light in the room, two different lights in the room, and then the lights together, and find the best value of P for whatever your camera is. And part B is to try do the same thing with these images. So you've got, this is a feed straight from my eyeglass, and on the left there's a oscillograph trace photograph, and there's a Nixie photograph. And you want to just combine those three images together using cement, and you'll get something that looks like this, which is kind of an artistically pleasing visual overlay. And so you can see through my eyeglass, and you can see the heart rate, or the heart waveform, and you can see the heart rate estimated from the waveform. So what you're going to want to do, and there's heart data here that I've provided. So context-aware heart monitor is the idea that overlays using augmented reality into the eyeglass. So you can see the electrodes placement here on the heart, and then this is what the overlay looks like. And so this is how it should look. This is the oscillograph. Actually, there's some better oscillograph pictures here of that cathode ray oscillograph. And you can see, for example, if I open that, you can open any of these images in a new tab and kind of zoom in, and you can see that looks pretty easy to see and understand that trace there. So now we can get that data overlaid, and this is a data set here, and a little bit of an explanation of the data set initial exploration. If you just go, there's no index in that directory, so if you just go here, you can see these are the DJI files. The first one is a time code where I just took a video of a clock, so we know what the time code is, and time code alignment, because this camera is in UTC, or Greenwich Mean Time. So you need to offset by the time to get it to line up with the data. Then from there on, there's data here. It's kind of boring at the beginning because I'm just running upstairs or whatever, but it gets a little bit more interesting. So you can grab a segment of video here where the heart data is relevant. This is just video straight out of my eyeglasses. I had to tie up my shoelaces so you can see the heart probably drops a little bit, but you can see some after drag on that. And as I'm running here, so you look at that data, and this is running down to the beach for a swim. And so you can see that data, and then what you're going to want to do is overlay something like this, like that oscillograph, like get GNU plot, see if you can get it to look similar to that, because that produces a familiar sort of aesthetic. See if you can take that data from the heart rate, and the data is in here. It's in that same directory. The data set's in here. So the data is right here, and also there's a CSV of the data. So this is the data right here. And you can see it right there. These are just numbers. There's two of them. And what I found is the best is this number minus this number equals the best number. And then plot that data. And when you plot that data, you get something that looks like this, and go through that data and look for the best. Find where the data is good and where it's bad. And find a good section and overlay that onto the video where it's good. But don't use white. Blue on white is the default. What you really need to use is a black background with green glowing visuals. And it'd be nice if you can make it look more like the oscilloscope. Like this looks pretty crummy, but try to get it to look, if you can, like the oscilloscope by making it blurry, make it blurry. Let me shut the screen save off here, go to the Jitsi, and make it, I'm gonna kill the screen save here, cancel. Make the data, make a fat line in a kind of dark green, and then make a thin line that's a really bright green right on top of it. What I usually do is I build up my plots. So I use GNU plot or something. I have a black background and I plot my function in a really fat line, like maybe 10 pixels wide. That's kind of a dark green. And then I plot a medium line that's about 5 pixels wide that's a slightly lighter green. And then I plot a 3 pixel wide line that's a really bright green, and then maybe a 1 pixel line that's white. And those overlay those on top of each other. And then it produces a nice glowing line that aesthetically looks pleasing, and it's easy to see, easy on the eyes, and then cement that right on top of the image. And you want to do that for each frame. And it might take a while, even if it takes 1 minute for every frame or something, leave it running all night and it'll produce a short few seconds of video. It'll give you an idea, because the purpose of this, we're not going to try and do it in real time right now, because if you're doing it in Python, it's not going to be real time probably. But what you'll do is you'll learn how to overlay and how to do augmented reality using cement to create this superposition, using the superposition properties of light. FFQ1 plus FFQ2 plus FFQ3. Say it'll be FFQ ITAP plus FFQ oscillograph plus FFQ Nixie. And to make it nice and fun, what I'm going to do is I'm going to photograph some of my Nixie tubes and post those photographs online. So I'll photograph Nixie tubes in the dark. So you can just use a library of Nixie tubes to display the numerals nicely, because they have a nice aesthetic. Or if you can come up with something artificially, like if you can generate the numerals, the same thing, put a black background, generate a really fat numeral, like say you have a number like 2, you know, the 2 in 72. So you draw the numeral 2 in a really fat 10 pixel wide line, then fairly dark yellow or amber, and then draw a 5 pixel wide 2, a little bit lighter, and then a 3 pixel wide, and then just maybe 1 pixel wide in white. So you have like a thin white line, and then on top of that a medium size yellow or amber line, and then a really fat red line. And if you do that right, it'll produce a nice glow, and it'll aesthetically look good, and it'll be very legible and easy to see. It'll look natural. The whole idea is what we call a natural user interface, NUI. I coined the term NUI, natural user interface, for a user interface that looks natural and feels natural and interacts naturally. So this idea of having things cemented together on a background produces a natural feel to it, a natural look. And I think it'll be a nice and I've got a request to post some lectures earlier. Yes, I'll try to work on that, Siddharth, posting lectures earlier. And if you have them for the midterm Monday, yes, you can present earlier, or we can arrange it a different time. So I think that's everything. Okay, so feel free to throw questions at me by email, and I'll respond quickly, and I will try to post some material sooner. It does take time to prepare. I'm struggling a lot with these computer systems and everything, so I'm trying to move as quickly as I can, but I'll try to get something posted soon, so you've got at least a good idea of what's happening and how to do it. Maybe I'll post. Let me know what's of the highest priority. Like if there's something that you need help on, I'll post right away, a short little how-to or a short little tutorial on something that people are having trouble with. I'll jump right to that and skip ahead. So that there's time, like as Siddharth had asked, there's time to get the information out sooner, especially if you can prioritize it. So thank you for attending, and We will connect shortly.